showing up tonight. Greatly appreciated. I am Jim Anderson. I am the chairman of the Florida West Coast Section's PACE group. PACE is dedicated to providing you with opportunities to learn more about the engineering profession. Right? And I think tonight we're going to do that in spades, as they like to say, because I'm very pleased to announce that we're going to have Mr. Butch Shadwell share with us some very interesting stories. And that's exactly what I asked Butch to do. So I've known Butch for 10 years or something like that. And every time I'd get together with him, I'd say, hey Butch, so what are you working on? And the story was always amazing, okay? So he owns his own engineering company, and people come to him with problems, and they say, we have a problem, Mr. Engineer. Could you help us out? The answer, of course, is always yes. And then the question is, now what's it going to take to solve their problem? And the answer, of course, is, since he's an engineer, he uses no, not magic, although that would be pretty cool. He uses math and science to solve problems, which is fundamentally what all of our teachers in school told us that we were going to do. But we never really quite figured out necessarily how to do it. He figured out how to do it, right? So I asked Butch to come and tell us actually two things. So Butch has done a lot of really cool projects in the past. And I said, Butch, I know you've done this many projects, but we only have about an hour. So could you just take a look at all the projects that you worked on and pick some of the interesting ones and come and share with us some of the background. What was the problem when they came to you? What did they give you? What was sort of your thinking process as you went through it? And what did you finally make or build or shape or do for them, and how did it turn out? Okay? And now Butch, okay, let's be honest, Butch is getting older. Okay? He's really, really tough. He's not that. But Butch has moved on to sort of another phase of his life. And this is what old people like to call, how can I change the world phase. And a lot of people sit at home and go, well, you know, that'd be great to do. I'll have to come up with something later on. Butch, because he's an engineer, has said, well, I'd like to change the world. And he's actually come up with a plan to do that. Not in an evil way, because oftentimes engineers do evil. No, this is not an evil one. But he's come up with some really cool stuff. He's involved in some very interesting projects that arguably are changing the world. And I asked him to perhaps spend a little bit of time tonight sharing some of the stories having to do with that. I think both of these sets of stories are really, really cool. So I'm very, very excited about being able to present Butch to you tonight. I think you're going to enjoy what he has to say. If you have questions, and you will have questions, can they ask you?
Anytime.
Okay?
Yeah, anytime.
Because you won't understand why he did what he did, or why somebody came to him, or why he made certain decisions. This is the time to ask him, because he's done it. He knows the answer. Okay? So if you're going to get anything out of tonight, it'll be from the questions that you ask and from the answer that he gives you to your questions. So when you see it, hand up in the air and ask your question. That sound like a fair deal?
Okay.
Are we done with your slideshow, sir?
Well, we'll let Rob talk. I'm going to say a few words.
Ladies and gentlemen,
Thank you, Jim.
Butch Shadwell.
I've had such a hype, it's incredible.
Yeah.
Well, I'm happy to be here this evening, and Jim and other people I know seem to find my career in applied science and electrical engineering interesting, and so that's what I want to talk about a little bit tonight. The slides, this is a big lion here. The slides I'm showing just now were part of my IEEE project in June of 2009. I was invited to a special meeting at the National Academy of Sciences in Washington. They invited about 150 scientists and engineers from around the world. And the meeting was called by the United Nations Foundation and IEEE, among some other sponsors. And they asked us if we'd be willing to spend some of our expertise for free, donate time, to figure out better ways to apply technology to help people in some of the poorest parts of the world. And I said yes. And they'd like me to be the international chairman of one of these committees. I'm the chairman of the Reliable Electricity Committee, and there are about 50 scientists around the world that work on my committee. In the course of this work, I developed some experimental power systems, and we've delivered several of them in the mountains of Nicaragua with the campesino farmers. I have some pictures I'll show you and also in Africa. And I go to remote parts of these countries. There's no electricity, no running water. In Africa, where I did these pictures, I was living with a Maasai village, and the toilet is a hole in the ground. So there's no shower. The food is quite different. So it's been very interesting. But I was able to provide electrical power for about 500 students in a Maasai school. and really made a big difference in the way they educate their kids in that area. These animals, I took all these pictures with a pocket camera, one of those little flat Canon ELS, you know. So there's no long lenses here. This is all pretty close.
Wow.
Yeah. Now this female right here, actually, I was taking pictures of these cubs, and there's a nursing female over there, and the other female didn't like me being so close. So she walked around, I got between me and the cubs so that they had a barrier. Yeah, I saw quite a few lions out there. Here you just, when you first started coming out to get between me and the cubs. This is in the afternoon. Lions usually feed in the morning, so these guys were very hungry this morning. But yeah, no long lenses. You saw pictures of the elephants, so it's really interesting. I had a Maasai person with my guide for this photo thing, and it was really very interesting. These are actually mongooses, but my camera didn't focus for some reason. There's some skull. That's a hippo skull on the bottom. You know, hippos kill more people in Africa than any other animal. They're very, very dangerous.
Hey, Butch, what are the mud huts that you showed us? There was
See that one yet?
There was little mud huts coming out of the ground.
Oh, that's a termite mound beginning. It's a small one. You're just getting started. Yeah, I don't know if I brought pictures of me, but I actually was in real full-size mud huts. The Maasai people, when they live in a traditional way, they're polygamists, and so the men buy wives with cows. And then when a wife gets married, her first job is to build her own house. And the way the houses are made is they're woven like a big basket. They get sticks that are about 3/4 of an inch in diameter, and they peel off all the branches to get these sticks, and they weave a big basket that's maybe 8 foot cube, 8 foot square, and about 5.5, 6 foot tall. And that becomes the walls of the house. And they spackle it with cow dung. And cow dung and urine mixed together, actually. And they say it lasts like 15 years. Wow. Pretty interesting building material. I've been to some of those houses. They don't smell that bad. After they've been aged for a while, the odor is pretty normal. That's a male water buck. It's pretty cool. So really what I was going to talk about tonight is some of my professional career. The title of my talk is Life and Times of an IEEE Member, the No Boundaries Career Option. I hope that makes sense to you all. This is me on a mule. I was riding up in the mountains in Nicaragua. This is one of the earlier trips I made into the remote parts of the world doing these special projects. But we're going to talk about engineering and electronics. But when I got into engineering, I had a career plan, and my plan was to make myself into the best one, literally the best one in the world. Make myself into a technical person, and this is for the benefit of the young people in the audience, maybe some students are here. The technical person they must have to meet their business objectives. And so you just have to study really hard. The strategy was to study everything, find the best mentors, and no challenge is too great. When I first got into the industry, I looked for employers that had really smart people from whom I could learn. And so when I found a really good mentor someplace, I did a job there, and I learned all I could from that person until I felt like I got what I could from that particular mentor. Then I get another job someplace else and find another mentor in a different subject matter area, a different range of expertise. Then I would go to work there until I learned all I could from those smart people, and then I'd go find somebody else. And so I was in the process of making myself into this individual I described in the first paragraph.
Butch, what gave you the idea to do this in the first place?
It seemed logical. You know, when I was in high school, for a few moments, I was actually concerned about survival. How would I going to make money to live and succeed in life? And but I knew I was pretty smart, and so I decided that I would never have an issue with survival. I'd always survive. So then the next question was, well, how can I use the gifts that God gave me optimally? And so becoming the best one seemed like the way to do that. Not only that, you get control. You know, as you make yourself into that individual that has the best skills and the broadest skill set, you become a rare commodity, and you can control your price and work on the things you like to do. I tell students all the time that if you really want to get the good jobs and make the most money, you make yourself into the person they have to have. In the universe of technical expertise, it's like a big continuum, right? There are people who don't work so hard, and they're at one end where they get less money and less fun things to do. And people who work really hard, they get more money and more fun things to do. And you get to choose where you want to be in that scale. It's a matter of how you bust your butt. I'm going to talk about some of the companies I've worked for in the different projects. I've made a series of slides with the highlights of some of the different projects I've done. Maybe all the slides together, and there are 4 different ones, have about a third of the major projects I've worked on. And so I'm going to quickly run through them. Many of them strike a note with you guys. We can talk about them some in more detail. And in my career, about a third of my work has been in medicine and biomedical technology. And this is a quick run through of the kinds of things I work on. The top one is nuclear medicine gamma cameras. I started out as a double E at the Naval Academy, and then I studied physics at FSU and optical electronics at Northwestern. And so and my whole career has been in applied research and development, new technologies, file packs, stuff like that. In this area here, we actually built cameras that could visualize organs working inside the body in real time. So we would inject patients with an isotope that would be metabolized by a particular organ. And by pointing the gamma camera at the body, we can actually see an image of those cells as they metabolize those compounds. And so it gives us a lot of diagnostic value. So many of you may have had some nuclear scans, and the technology might be some of the stuff that I worked on many years ago. Facial bone reconstruction. A project I had was to come up with a thermal probe that would allow doctors during surgery to change the shape of these small brackets. They had brackets made of a resin. And so when you have a facial injury and break the bones in your face, the bones are rather heavily contoured and small. And so they make these little resin brackets, and they want to be able to shape the bracket to match the contour of the cheeks and so on during the operation. So we came up with a method to do that. And the current problems we're talking about solving here are the probe has to be highly regulated in terms of temperature. We don't want to damage tissue in the course of the operation. And it has to be a low thermal mass and a few other things that are important in this surgical environment. Dental descaler.
Hey, Butch, on the facial bone reconstruction, do you have to have like FDA approval for something like that?
People were going to make it and sell it.
Okay.
I'm just solving technical problems for people.
So you're making like a tool for like one doctor who's doing facial reconstruction, and so it doesn't really need to be FDA certified? Is it?
No. Eventually, to be used on patients commercially, it would have to be FDA certified.
Okay.
I initially didn't get involved with that. I will just solve for example, this one down here on the new brain scalpel here. I'm working right now with a company in Salt Lake City, Utah, developing a new scalpel for brain surgery. And it involves different sciences. It involves some physics, so ferromagnetic materials, and stimulating it with RF energy. And again, we have to regulate temperature and power output, and go into different tissue densities. You only get different amounts of cutting. This for cauterizing. One of the unique things about the scalpel is that we can cauterize blood vessels and bleeding tissue without putting any electrical current into the patient's body, where most cauterizing tools today, they actually pass current to the patient. And so it's transcranial spectroscopy was about using differential infrared sensing to look at the oxygen infusion in the brain. So we can tell what parts of the brain are most active by looking at the oxygen uptake, which we can measure through transcranial infrared energy. That means actually shining light directly through your scalp and skull, so there's no invasive anything, there's no radiation. no MRI. You just shine some light through the skull. Laparoscopic instrument tester was about making sure the cauterizing tools didn't cause accidental burns. CO2 monitor, this is an interesting one. The CO2 monitor, a doctor came to me and said, well, you know, in the operating theater, we have all these instruments, and they're all flashing lights and beeping all the time. And it can be quite distracting for the anesthesiologist and the people in the room. And so he had an idea, well, he would like to get a different kind of feedback about the CO2 concentration in the patient's exhalation. And so we had an off-the-shelf instrument that measures CO2 already, but again, it had flashing lights and dials and stuff. And so what I did was I created a synthetic breath sound. So it sounded like a person breathing. And we would modulate the breath sound to give the doctor a cue that the patient was in distress. Like you'd have a stutter breath. You know, different things would happen to give the doctor an audible cue that sounded like a patient in distress. So rather than get flashing lights and alarms going off, he would get a cue that sounded more like a person. But it was all synthesized. Of course, the patient's asleep. Irrigation monitor was just a device to measure the fluid flow from post-surgical irrigation, and to be able to measure weight to a really fine degree. I used a strain gauge technology and a 22-bit A to D converter and a special chopping differential amplifier. I'm not sure if you guys have heard of these things, but in linear amplification, the latest technology are chopping amplifiers where we continually reverse the terminals on an op amp. And so by reversing the terminals back and forth and integrating that difference, you can subtract out the input offset error. And so we can actually reduce the error to a very, very small amount by using this chopping method. And complex mobile brain test, that's a device I designed back in 1974, 73.
Hold on. You didn't go over the dental descaler.
Oh, the dental descaler, okay. The dental descaler was an interesting project. People came to me and they said they wanted to be able to make a descaler. A descaler is a device they use for removing calculus from teeth. You know, if you have plaque over time, you get calcium deposits on the outside of the tooth surface. They refer to that as calculus. And they have technologies already that use an ultrasonic transducer to stimulate a stainless steel probe, and it oscillates the crystal structure of the calculus makes it shatter. Okay. So the thing is, though, that these probes, because of this oscillation, generate heat. When you have friction between the tool and your tooth, it's going to get warm. And so the tool requires irrigation. So if you've ever had your teeth cleaned, you notice all that water going in while they're doing the cleaning thing. It's to keep the temperature regulated in the tissue because of the heat being created by this piezoelectric transducer. So the question was, could they make it cordless? And so it was easy to figure out how to get enough electrical energy to drive the piezo transducer, but the problem was the heat dissipation. And so in this particular problem, I had to do something about physical chemistry because I did calculations on the specific heat of a certain amount of water. And I realized how much water I had to have in the little reservoir in the handheld component to be able to dissipate the amount of heat generated in the normal time space. And so that was one of the unique things about that one, was taking advantage of my knowledge of physical chemistry to be able to dissipate that amount of heat in the tissue before it damaged everybody's mouth. This is some of the robotic stuff I've done. A lot of my work has been in robotics and artificial intelligence. This is back in 1984, I think. I invented a new kind of mouth control. In animated characters, robot people, they have amusement parks and so on. They often have a person backstage with a microphone. And they'll actually converse with the attendees at the park by a person in the back just answering the questions into a microphone. So we have to have the robot mouth those words correctly to look like he's actually speaking or she's speaking. And so I came up with a circuit that would actually take the spoken word power envelope and convert that into signals for it's actually a pulse width modulated signal for a pneumatic actuator, for an air actuator, actuating the mouth. It was kind of interesting project. You know, the first thing I did was I took the signal that came from the microphone, amplified a little bit of course, and filtered it out. So we had a particular bandwidth I was interested in. And then we did a square. When you square a bipolar waveform, what happens to it? It all becomes positive, right? And so I did a mathematical square, make it all positive, and And then once it was all positive, I just integrated it. And I had two different integrals, actually, different in time. And so I subtracted one integral from the other integral, and that became the drive signal for the mouth, which then turned into PWM. Does that make sense, everybody?
That's the way I would have done it.
Yeah. Let's see what else on the list. 128-axis robot control system. I designed that back in 1985. Back then, we were using a Z80 microprocessor, but it was kind of interesting. And the device allowed them to do all the editing of the robot manipulations on the device itself.
Okay. I'm dense, but I'm having trouble figuring out what are 128 axes?
A big show. We may have a bunch of robots on stage dancing and singing, and lights working, and curtains working. And so I have one control unit that manages all these robots simultaneously.
Okay.
In fact, those robots, these two controllers, the 25 and the 128, they've been installed all over the world. They're operating hundreds of robot characters all over the place.
In the entertainment setting?
Entertainment, that's right. They're singing and dancing, working the curtains and lights. It's really kind of fun. It's like being in showbiz, but it's engineering. It's really something to do. Machine vision. I worked at CSX for a while. I was actually the chief scientist in an R&D like skunk group. And one of the problems that they gave me to work on was automating what they call a hump yard. You guys been to a hump yard? Anybody want to go to one? But the hump yard in railroad vernacular is a place that has a hump in it. It's a hill. And if you can imagine, trains are like packetized data, right? They have all these cars, and they have contents inside of it, which is valuable. And so they put a train together, and they move it from one node to another. And then at each node, the train gets decomposed, and then all those packets are resorted to go off in other directions. And so the way that happens is they call it a class yard or a hump yard, and the train comes up to the hump, and actually the train is pushing the cars at this point. When they get to the top of the hill, there's no tension on the coupling, and so they decouple the cars at the top of the hill. And then the cars roll down the hill, and they gather momentum, right, kinetic energy. And what this computer system did was, first of all, it gathered data on which cars were in the train and where they were supposed to go to. And as they were decoupled, the system would weigh the car, it would measure the airspeed, it would measure the rollability of the car, that is the rolling friction of that particular car. And then it would compute exactly how much of that momentum, the kinetic energy, had to be removed in order for the car to couple at the correct speed when it went down the correct track. You know, we may have 30 or 40 different tracks that the cars go to as they exit the hill, go in different directions, right? And so we're building like 32 trains. And so it was a really interesting calculation because we had to actually manage a device called a retarder. And a retarder, what it does is, it's a big metal thing that's worked pneumatically, and it comes up and it grabs the car wheels from the outside, and acts like a brake. It takes energy out of the car. And so when you measure the rollability of the car and all these things, you calculate how much energy is required to get to the car that's already in the track. Like, you may have cars all the way down at the end of the track, and you may have cars closer to the beginning of the track. And so the distance is varying all the time, too. And so if the car couples at greater than 3 miles an hour, you can damage the coupling mechanism. If it's going slower than 1.5 miles an hour, it won't couple. It won't actually latch. And so you had to control the speed very precisely. And all that happened up at the head end. And so you had to be able to calculate in advance exactly how much momentum it took to get all the way down to where it's going to couple and hit at the right speed.
So I would guess then that before you came along, they would have a brakeman on the car.
Well, that was the original way they did it way back.
Way back, and he's got a wheel.
Yeah.
And he adjusts the speed so he can tell it's going to hit the next train car just exactly right.
That's right. It's all done by
only now you're doing it by computation.
Right. Well, now actually, let me add one more thing to what you just said. We did it by digital computation, but prior to my device, which I created for this particular project, they had an analog computer there that did a lot of these things, but not quite as well. And it was actually a vacuum tube analog computer. And
what are they?
And they were using these vacuum tube analog computers as recently as the late 80s. They're still depending on vacuum tube analog computers to compute this energy problem in real time.
Question.
Yeah.
What about in this process? Did you have anything in the area of RFID then
Not then, that's done a project later on. In fact, the next thing on the list here.
I'm just judging the time frame.
Yeah, this one, machine vision here, when I was working at the same company, after I did the automation of the computer project, in North America, there are roughly 7 million pieces of rolling stock. That's cars and engines that move on the tracks all over the country, roughly 7 million. And they all are different, but they all, some of them look a lot alike. If you have box cars, for example, you can have 1,000 blue box cars that are built exactly the same way. And very small differences being like the numerals painted on the side perhaps. So they had this need to keep track of which car was where, and so they need to be able to identify cars. And the technologies that have been tried up to that point included barcodes attached to the side of the car, and there was people, at that time they were experimenting with using RFID tags on the cars as well. Well, one of the unique features of railroad cars is that when you move commodities in the north, where it's quite cold, things can freeze. And so, for example, they have gondola cars that carry coal and ore from one place to another, and then when it snows or rains, that gondola gets full of water or snow that can melt, and then it turns into a 220,000-pound ice cube. and so because it's difficult to manage like that, they have a thing called a tippler, which actually just dumps the car over and dumps it out. So when you get a 220,000-pound ice cube falling out of the car, it destroys everything underneath it. And so rather than that happen, they have to turn it back into a slurry, some kind of fluid material. And the way they do it is by using what they call a thaw shed. And so they have big sheds that have fire shooting out on both sides of the shed, and they drive the train through the shed, and the fire melts the ice and snow in the cars prior to being dumped out, so that it dumps out like a fluid other than a big ice cube. But they can imagine the effect these flames would have on an RFID tag attached to the side of the car. So there was a number of reasons why at that time they weren't planning on using RFIDs.
But wouldn't those flames burn off any painted on logos and numbers and stuff like that?
It's had an effect on everything. Right.
Yeah. I would have thought, I've seen these cars where they got things at the bottom, they just dump straight down. You have to turn these over, you're saying?
Yeah, the gondolas they use for coal and ore, they would just put on a tipple. They actually have a device that grabs the wheels and grabs the car and rotates 180 and just dumps it straight out. As it's rotating, it pours out slowly through like a little plenum thing, you know. But if it's frozen, then it won't go through the plenum.
Yeah, sure. No, if it's frozen, of course not.
Yeah. So, well, the problem with keeping track of cars is that I decided we could do it with robotic vision. And so I went to Carnegie Mellon University in Pittsburgh at the Robotics Institute there. And I got a few professors to work with me on the project. And we invented a method that we called the fingerprint, ID fingerprint. And what it came down to was I designed a high-resolution scanner that would give us a non-parallax image of the side of the car in pretty good detail, like 1/4 inch pixels, for the entire surface of the car. And then we did a spatial derivative, looking for interesting variation in intensity or color on short image operators, maybe 120 pixels at a time. And so those became image operators. We would do maybe a few hundred of them on the whole surface of the image. And then we would convolve those later on and use convolution to properly identify which car was which.
If somebody spray painted the car, would you still be able to identify it?
That's a good question. In fact, we would do cars that were directly out of the paint shed. Now, the thing is that cars that have just been repainted have a very nice numeral painted on the side. I say nice with a caveat attached to it. And that is that when they paint numerals on railroad cars, they're segmented. They have those stencil they use, you know, and so the characters are not uniform and continuous. And so one of the things we did was I came up with an idea to do a low-pass filter on the image of the characters before doing the OCR, optical character recognition. And so we used pretty much the standard optical character recognition using a fuzzy logic, neural net. We use a neural net for OCR. But the neural net OCR was working after the low-pass filter on the image data. Interesting stuff. Okay, what else do we have here? Yeah, this machine, by the way, I built one here in Tampa. This was the first test I was here in Tampa. And we were examining cars that came out of the phosphate mines that are close to by here. And we had 100% performance. Never failed to identify a car, whether it was raining or sunny or night or day, didn't matter.
But these were clean cars.
Well, the thing about phosphate cars is that they get rusty, they get cloudy on the outside. In general, the letters are almost illegible.
So you're doing this on that kind of car?
Yeah. In fact, the system worked better with cars that had a lot of graffiti. Because we did this interesting, the derivative along a spatial distribution. And so if you had a lot of weird things like rust spots and graffiti, all those contributed to the signature for the car. The fact is that we only had to involve a few operators to know a car specifically because convolution is a very strong discriminator. And so we didn't have to have very many of them matched to say, yeah, we know what car this is. One of the things I invented to go along with this machine vision problem was a device to actually measure the distance from the ground to the bottom of the car. I wanted to get an image of the contour of the bottom of the car to use it as another axis in my database for identifying specific cars. And so I used a Hall effect sensor. And if you can imagine, I took an annular ring magnet and I had a post in the center. And so the lines of force are going from the center post all around to this ring around the outside, okay? And so when there's no other metal in the vicinity, the lines of force are concentrated kind of low, directly from the center post to the outside down the annular ring. But when you bring metal around, it distorts the lines of force and makes them go more vertically. So I put a Hall effect sensor directly above the center pole, and as the lines get distorted and made more normal to the surface of the Hall effect sensor, I got a better Hall effect signal. You all understand Hall effect sensors? I'll tell you real quickly. A Hall effect sensor is basically a conducting plate. It might be made of metal. And there's a thing called the right-hand rule in electricity where if you have an electric field going in one direction, the magnet field in one direction, the electrical current gets in another direction. Well, we had lines of force that were normal to the surface would force the electrons to go to one side or the other, depending on the direction of the magnetic field. And so we could actually measure the difference of potential from side to side on the plate as the magnetic field through the center appeared. So we could get an analog signal that told us how far away the metal was. Now, I'm sure you all know that magnetic fields of this sort obey an inverse cube law, right? It's not inverse square for magnetic fields. And so with inverse cube law, the field gets depleted rather quickly as you get away from those poles. Interesting problem, anyway.
So, Butch, real quick question about this. So it looks like you have a great deal of experience in building robotic devices. Yeah. Now, I'm not sure if you're aware of this or not, but the IEEE in Region 3, which is the southeastern USA, every year has a show called SoutheastCon. And SoutheastCon, one of the big parts of that is various colleges are invited to have student teams enter a robot designed to solve some particular, sort of challenge, shoot ping pong balls through a loop or find multicolored things. Have you ever considered entering that contest? They have a separate portion of that contest.
I've thought of it a lot of times.
It just seems like you could clean up. But you could show the kids how it's supposed to be done.
I just get sort of busy, so I don't have time to know how it goes. But I have done a lot of talks on this stuff. I speak at a lot of universities in the Southeast to give kids a head start on their robot projects. Help them understand how to design autonomous systems.
We have a few high schools around here that could use your assistant expertise.
Oh yeah. Well, I'd be happy to help out if I can. It depends on who's covering my mileage. And,
we're just 200 miles away from it. So.
Yeah, that's kind of a long drive for me. Yeah.
Well, unfortunately, one of the problems that you have to consider in your budgeting is that high schools don't have that much money.
There you go. You have to have a fundraiser down here,
there you go. That's how it's played.
Now the thing is, when I get these kinds of problems, all kinds of interesting things to figure out, you have to do what's called problem decomposition. And I think that one of the advantages I have over many of my peers is that I approach problem decomposition from the perspective as an applied scientist rather than an engineer. I look at the fundamental forces involved. I try to understand everything from the most fundamental perspective, and then figure out the best vector to a solution in that realm of understanding. As opposed to trying to apply off-the-shelf engineering solutions, I look at the physics first and then find the correct thing that solves the problem.
What's your education background?
Start out double answers to physics.
So here's a thought. Perhaps somewhere toward the end, one of the projects that you told us about, and walk us through how you would approach that with looking at it from the fundamentals of physics as an example.
Okay.
That's something reasonable?
Sure.
Okay.
See if we can do any of these, but let's see if we have some more interesting.
Let you pick whatever you think. We don't know what you got, so.
Okay, here's some industrial projects. Fluxgate magnetic field detector. Have you guys ever heard of a fluxgate sensor? It's a method for measuring really weak magnetic fields. You know, the magnetic field of the Earth is on the order of a few Gauss. Gauss is 1/10,000th of a Tesla. But anyway, it's a very weak field, and the fields I was trying to measure are actually weaker than the Earth's magnetic field. So I had to subtract out the Earth's magnetic field to get an accurate measurement on these other fields they wanted me to measure. It was an interesting problem. The reason they have you doing this problem with the fluxgate sensors, there's a company that makes water meters. You know, they have the water meter outside your house with a little dial on it and all that. Well, these guys are making a water meter like that as the water flowed through the meter, it had a little magnet that was spinning. And they were interested in being able to monitor that spinning magnet at a distance. And so if you can imagine, again, we have this inverse cube law thing, right? And so as you get just a few inches away from the meter, the field is quite weak. And so the challenge was to come up with a method to measure this field at several, I think it was probably 6 inches away, which is a pretty weak field. Solenoid current regulator, I have PWM, the current flow through an activated solenoid. They had a big solenoid on an earth-moving machine, and they wanted to regulate the amount of heat dissipation. And so I did the problem for that. Airflow volume, it was a central AC system. And we can talk about this one from the physics perspective. There's a company that hired me as a consultant, and they manufactured all kinds of HVAC components, including these big electrically operated dampers where they can control airflow. Right? And so in commercial buildings, they may have one central AC system that provides conditioned air to all of the renters, all of the people that are renting spaces in the building. And so the company that makes these systems wanted to be able to bill each individual renter in the commercial building for how much conditioned air they use. They use a lot of AC, a lot of heating, whatever. And so they had to come up with a way to measure exactly how much conditioned air each one consumes. And so when you adjust the thermostat on the wall, you're actually changing the damper setting in the ductwork so that you get more air or less air. Now that, of course, if I just looked at the damper angle, I couldn't really know because all the other dampers in the system are going to change the back pressure. And so the airflow volume will vary continually as things happen in the system. So again, looking at this problem, if you can imagine you have an air conductor, a big pipe, and air's flowing through there. And if you study a little bit about fluid dynamics, you know that there are going to be eddy currents inside this conductor. And any little protrusion, a screw head, all these things are going to cause turbulence inside the conductor. And the result of that is you get a non-uniform distribution of the air mass. So there'll be certain places around the circumference where the static pressure is higher or lower, depending on the velocity of the fluid at that particular point in the conductor. Does that make sense? Okay. So what I came up with was a way to say, well, I got this I can't just put a regular static pressure measuring transducer because wherever I stick it, it's going to probably have the wrong pressure most of the time. And so what I did was I took and I got a piece of inner tube, rubber inner tube, and I drilled holes all around the air conductor, the big air pipe, whatever they call those ductwork things. And then I put the rubber thing around it, and I put straps on both sides so that it became a sealed bladder. And so essentially what I did was, by putting holes all the way around the air conductor with a rubber bladder on it, I used the rubber bladder to integrate the signal, okay? So I was integrating the signals from all of those holes around the entire conductor so that regardless of the irregularity of the airflow, I would look at the actual average of all of them to get the static pressure. And then I put a strain gauge around that to measure the amount of force on the rubber bladder. I had a strain gauge tube wrapped around that. You see, I started like all you guys did. I started as double E. But the thing is, you have to think outside the box sometimes. You have to create technologies that haven't really existed before. Talk about that. Well, the last one here is kind of interesting. A customer came to me and said that we need to be able to identify what kind of fiber there is in carpets. It sounds like a weird kind of problem, but they were interested in learning what kind of fiber was in a sample of carpet because of insurance claims. Insurance companies insure buildings like this one, and if they have a big flood or a hurricane hits and they have to pay for having the carpeting replaced, the insurance company wants to replace the carpet with the same value carpet they had originally. And so it's important to identify exactly what kind of carpet you had. And one of the parameters of identifying the value of the carpet is knowing what kind of fiber you have in the carpet. The fibers are generally synthetics. And so they wanted me to invent an instrument they could use in the field, where some person in the field could take a small handheld instrument and put it on the carpet and have it analyze the chemical composition of those fibers on site. The way they do it prior to this invention is that they had a big spectrum analyzer that weighs like 500 pounds. It sits on a static, on a vibration-free table back at the lab, and they charge a bunch of money to use it. So it can't be used in the field at all. It's much too sensitive an instrument. So I came up with a design to do the same function with a little handheld instrument that costs a tiny fraction of the amount, and it's not sensitive at all to being knocked around. You keep it in the toolbox if you want to. But it allows them to actually measure the chemical compounds in the carpet from just sticking it on there. Basically, I'm looking at the absorption spectrum of those compounds at certain wavelengths to determine whether it's nylon or rayon or some other synthetic fiber that they use in carpets. So you have to think outside the box.
Oh, no, you don't, Butch.
Yes, you know.
You got to cover the electronic lobster lure.
Yeah, I'm going to get into that one on. But did I pass it already?
You did. Go back. There you go. See, it's about halfway down.
Oh, yeah, electronic lobster. This is a good one.
Yes. Every time we buy one.
I don't know where the people come from, but they come to see me. I don't do any marketing. You know, I've been working as a consultant now for 20 years. And prior to that, I did some consulting work on the side. But people find out about me, and they come to see me with these interesting problems. In this case, there's a group of people in the northwest U.S., and they're heavily into the lobster industry. And they were interested in creating a lure to attract lobsters to lobster traps, rather than bait them, have a synthetic electronic lure. And so the idea was that I would create some little lure that could mimic the sound of lobsters like making out. Some activity going on. They could get lucky if they went this way. And so the way it worked was I went on the internet and I found some nature site where they actually had a digital recording of the sound that lobsters make. And so I did a spectral analysis of that, and I got this whole lot of information about all these noises lobsters make for them. Morris, you know. And so with that information, again, this is a fishing lure, right? So it can't be very expensive. You're going to buy these things by the thousands, and you can't spend a lot of money on them. And they have to be small. I made a capsule that was maybe 4 inches long and about 1 inch in diameter. And they actually made a little rubber lobster suit for it. This capsule and a rubber lobster suit. And but the way it worked was, again, to keep it inexpensive, I used a really cheap little processor chip. The chip costs 15 cents a piece, 20 cents. And to give you an idea, this particular chip had 512 words of program space, not kilobytes or megabytes, 512 words of program space. And it had 33 bytes of RAM, which you could use for data space, 33 bytes of RAM. And it had this complex transfer function for this noise that lobsters make, right? And so basically, something that I've developed a knack for over the years is being able to convert complex transfer functions into integer math, so that I can do them with a lot fewer machine cycles and on low-priced processors. So in this case, I got this little cheap little processor chip to synthesize this complex waveform of lobsters and put it into a piezo transducer that would generate sound from that waveform. Now, one thing you guys may already know about piezo transducers is that the natural frequency of a brass disc that's about 3/4 of an inch in diameter is quite high. Natural frequency being 3 or 4 kilohertz. And so when you look at lobster sounds, they're much lower frequency, several hundred hertz in that range. So in order to get energy out of this piezo device, I did one more thing. I did a dot product, again, with this integer math method of mine. I did the product of the lobster we formed with a 3 kilohertz carrier. So basically I modulated a 3 kilohertz carrier so that the 3 kilohertz would run the piezo at a high efficiency point. But in fact, when you put it through the filtering of the water interface, you get a nice slow sound, and it seemed to work pretty good. The lobster dug it, you know. And when I designed this thing, I put 2 little stainless steel screws on the outside, so when it went into the water, it would activate the circuit, it would run. When it came out of the water, it would turn itself off. Whenever the battery went dead, you just throw it away. It's disposable.
What do they call it?
I don't know. I just make the prototypes. Basically, all these problems, most of the companies that hire me, they actually have their own engineering staff. Most of them do. And so they hire me to solve a hard problem, and then I'll build a prototype in my lab, and I'll send them all my calculations and schematics and whatever, and then they do whatever they want to. I don't take any risk. I basically, I enjoy solving the hard problems and making the first one, and then I give them the first one, and they make money on it if they're good at it.
So you don't have any patents on this?
Well, I have a number of patents with my name on them, but I don't have any of the profits from the patents. But see, the thing is, I have some friends of mine who do similar kinds of work, and some of them have tried to maintain some percentage of ownership or some part ownership of the patent rights, which would be a reasonable thing to do. But then they're continually in an adversarial relationship with their customers. They're arguing about how much things actually cost, what was the actual net profit, all these things. And so what I do is I just charge a lot up front. You know, I charge more than the other guys do. And so they get to use my 40 years of experience and expertise. And if they make a profit on it, great. But they're taking all the risk. And so I don't take the risk. Does that make sense? Yeah, actually, I filed on the order of 70 patent disclosure documents over the years. But right now, I've only got 6 patent numbers. Patents are an interesting thing, you know. When you patent something, you're basically disclosing to the entire world exactly how you do it. And of course, in the world, there are countries that don't subscribe to our patent treaty. So they're not constrained at all by patent treaties. So companies, many of whom I work with, understand that it's much better in terms of their profitability to keep everything as secret as possible. One company I worked for where I was developing the optical smoke sensors, I think I might have already passed that. Let's look next slide. Rather than file patents on the optical sensors I designed for them and the combination of nuclear and optical sensors I designed, they just geared up their manufacturing line to be able to produce it faster and cheaper than anybody else could and just flood the market. So they got name brand identification right away because they want this kind of sensor to get it from these guys. And then what about reverse engineering stuff? We do things for that, like for a reverse engineering prevention, we'll order the parts without any labels on them, so the parts just come blank, or they'll have fake numbers we make up to put on them, stuff like that. And working for that company is kind of interesting because that company, everything I designed, they would actually make $2 million the first year, and then it goes up from there. So whenever you're designing some circuit or system, and they're planning on making $1 million of them a year or more, the design gets to have some very critical aspects. For example, when I designed those kinds of things, I would actually write a spec sheet for every component, every resistor, every capacitor, every transistor IC. I wrote a very detailed spec sheet as to exactly what I had to have in terms of performance of those parts to meet the specs for the entire system to work correctly. By doing that, we could give these spec sheets to part manufacturers and say, we'll take your fallout, anything you got that meets these minimal specs. And so by being able to buy fallout from their manufacturing line, we didn't need to have them meet all the specs for their part, just the specs that mattered to us. And so we could buy fallout from the manufacturing, we get them really cheap. We were buying ICs for like a penny a piece and stuff like that, because it would have been zero cost, I mean, zero value if we didn't relax the specs to meet our orders. So, and again, when you're doing millions, if you can save a half a cent here and a penny there, it makes a big difference. So, you know, that's another thing about engineering they don't teach you too much in many schools anyway. And that is that if you can't hit the price point, you know, whenever you design some new technology for your company to sell to somebody, it can't cost more than X number of dollars, otherwise there's no market for it. Nobody's going to want to buy that thing. It's too expensive. And so the entire challenge about being an engineer in that environment is, can you hit the price point? Can you meet the expectations of the customer within the price range that they're willing to pay? If you can't make your system function to meet their expectations within the price point that makes it profitable, then you don't have anything. It's not worth anything at all.
Do you ever run into a situation where your customer has a competing product for your customer out there, and your customer wants a version of it that will get around the patents on the one out there, but do the same thing?
Yeah, sort of. I've had people ask me to reverse engineer stuff for
It's
them.
not quite reverse engineer, because that gets you to do exactly what they did.
Yeah.
That's useful, but not as good. But what if you say, all right, here's the end behavior, and I'm going to find a way different than what their patent does?
Yeah, and I've done that too. In fact, I do a lot of patent writing for other people. You know, because I've been involved in the patent process for a long time, I've written many patent applications and stuff. I can use my expertise to read patents and find ways to achieve the same outcome without hitting a particular claim. For those of you unfamiliar with patent laws and stuff, when you have a patent, you have a list of claims, and really those claims are the mechanisms by which you have value. Okay? When you do due diligence on a patent, it comes down to analyzing each of those claims and exactly how many dollars each one is worth. When you file a patent application with the patent office, there's an examiner there that's going to try to eliminate as many of those claims as they can. And sometimes you put in extra claims that you know they're going to eliminate, so you end up with the ones you really want left over. Patent examiners are not necessarily really the sharpest pin in the stack. You know? Many patent examiners are fresh out of college. I mean, they're pretty bright people maybe, but they've never actually made anything of value. And they get snowed really easily, and they make a lot of mistakes. So getting patents is an interesting process. It takes forever these days. Today, if I filed a patent for an electronic device like one of these things, it would take a minimum of 2 years just to get the first office action, which is where they say, I looked at it. And then after that, it could be another year or so before you actually get a patent. So if you need to get a patent number in order to get your business going, you're talking about like 3 years before that number comes into your hand. This first one's kind of interesting. The guy came to me, wanted a device to make dogs shut up. They had yappy dogs in their neighborhood, I guess. So I read a few papers on this, and it turned out that there were some ultrasonic frequencies that dogs would respond to. And the unique thing was not just that it would be a particular range of frequencies, but they had to be modulated a certain way. And so I created a little circuit that had a little processor in it. And this processor synthesized a rather complex waveform where I created an ultrasonic waveform that made dogs behave better. It really worked. I sold a lot of them. This combination of detector is kind of interesting. Again, the problem is detecting smoke in this case. And products of combustion have many interesting physical properties. The typical smoke detector you buy at Walmart for like 10 bucks, they call it an ionization detector. It's actually a nuclear ionization detector. Those detectors have a small piece of americium-241, it's a radionuclide, that gives off alpha particles. And so all of you probably have radioactive sources in your house right now that you don't know about. Now the alpha particles are used to ionize air in a particular chamber, a little chamber here. And the chamber has two parts. It has an upper part and lower part with a metal plate in the center, and then americium on the center plate. And so the air is ionized on both sides, and one side of the chamber is exposed to the outside air, and the bottom side is not. And so when you get smoke particles into the upper chamber, it traps some of those ions as they migrate in the electric field. Now when you put a 9-volt battery into your smoke detector, that battery is being used to create a 9-volt electric field on this chamber. And so those ions are propelled physically by that electric field. And you can measure the potential on the center plate with a high impedance voltmeter, electrometer. The input impedance of that electrometer is on the order of a tera, 10 to the 12th ohms input impedance. You can imagine that. You guys know about electronics.
Dampness gets in the way.
Sorry?
Dampness.
It can, yeah. A lot of things will affect that. In fact, what we do in the detector if we make like that is that we take the center conductor plate, which is mounted in a big plastic thing, and we have that wire come directly out, and we take the pin on the IC and bend it up, so that the IC pin never touches the PC board at all. The pin is welded directly onto that center conductor plate in the ion chamber. And so if you measure that voltage in the center, when you get smoke on one side, that becomes a higher impedance and the voltage changes on the center plate. And you can measure that analog voltage change and that doesn't there's smoke in the unit. Well, the thing about that is that this ionization phenomenon, it works much better on new smoke than old smoke. If smoke's been traveling through space for a while, its capacity to trap ions goes down. And so you can get old smoke into the chamber is much less sensitive. And so we wanted to create a smoke detector that would be sensitive to both old smoke that travel a longer distance, as well as new smoke that travel a shorter distance. And so I created an optical sensor using forward scattering physics. You guys probably heard about this, I'm sure. Rayleigh scattering and Mach scattering, remember those classes in their physics? You can actually calculate the forward scattering angle based on the wavelength and the particle diameter. And so I calculated some angles and stuff and came up with a sensor that had a really high signal-to-noise ratio based on scattering of infrared light off of these smoke particles. And it didn't matter how old they were because it would still scatter the same way regardless of the age of the smoke particles. So we combined the two together. I built a detector that had both the ionization chamber and the this forward scattering sensor, optical sensor, in one container. And one of the design constraints was that it had to run for 2 years on a 9-volt battery. So how do you build all the analog circuitry, all the digital circuitry, all the high-intensity infrared light to run for 2 years on a 9-volt battery? Interesting challenge. And again, hit the price point too. You know, smoke detectors can't be very expensive. People won't buy them. So I think the BOM had to be $7 for everything. The case, the PC board, all the sensors, everything would be $7 total. And to hit the price point.
When you're dealing with something like that,
I'm sorry?
when you're dealing with something like that and you're dealing with extreme low cost where you can, you're going to introduce your errors in what you're measuring. How do you deal with that?
Well, in that particular kind of device, a smoke detector, it has to do with human safety. And so in order to get UL listing, it has to never fail in a way that makes it less safe. And so what we do is we design it so that it's continually self-testing, and we design it so that if anything does fail, any particular component fails, it fails towards more sensitivity and a false alarm. And that's what I did. I spent many months actually doing calculations on every component, calculating probability of failure of which modes. And then when we found a failure mode that would reduce sensitivity, we changed the design so that it actually increases sensitivity or causes an immediate alarm. I did a similar process in the military. I did research for the Air Force for a few years in electronic countermeasures. The challenge there was during the Cold War days. And we got intelligence from U-2 planes and SR-71s, as well as some ground intelligence on Russian threats, different kinds of missiles and radars they were using. And so we would analyze this Russian threat information and figure out types of electronics we could design to put in our aircraft to protect the pilot against the danger from those threats. And it was really interesting, very challenging stuff.
Which you got about 10 minutes left or so.
Just to mention quickly, I've done some work for NASA on the Space Shuttle launch pad. I work for the Army on the Predator UAV flight control modules. I mentioned active electronic countermeasures, real-time thrust simulation. That was interesting. Back in 1978, I designed a little digital math processor that could do a linear interpolation in 50 nanoseconds. It's pretty fast. Wow. And if you imagine all the things you do in linear interpolation, then you have to subtract and multiply all this stuff. And basically, the reason for that was I wanted to be able to synthesize the power load of an enemy radar, occulting radar, in real time, so that as the power load passes your receiver, you'll be able to see the exact amount of energy that you would normally get from the real power load. And so I'd be continually modulating the attenuator to reduce the energy so that I would see the exact power load as it passed by. Okay, humanitarian projects. This is some pictures from the meeting with the National Academy of Science in 2009. That's one of our slides there, and that's me and Carl Persick. That's where they elected me to be chairman. This is the first experimental system we designed. I designed the circuitry, by the way. It's got some interesting features. Over on this side, those are all LED status indicators. In order to make it so that it would be user obvious, this was going to parts of the world where there are no technical people. In fact, people are generally illiterate. And so you have to build systems that would be self-managing. So this has intelligence. It can manage itself regardless of the technical savvy of the user. And so behind these LEDs, we actually had little pictographs. So like if it was time to clean the solar panels off, it would light up a little picture of a guy cleaning the panels off. Stuff like that. These are the main power output nodes here. These little yellow things are PTCs, positive temperature coefficient thermistors. You guys know what those are? They're thermistors, which of course are resistors of varying temperature. But they have positive temperature coefficient. So as the load begins to draw excess current, it begins to warm up. As it warms up, the impedance increases very quickly. And so if you have a malfunction in a load, then the impedance shoots up to like 100,000 ohms. You just have a tiny amount of leakage current through them. And then in order to reset the device, just turn the current off for a little while. It cools down to its normal temperature, and you're operating normally again. It's a self-resetting circuit breaker based entirely on thermal properties of that PTC material.
Hey Butch, there seems to be a chip in the middle of that particular circuit board. Is that like a CPU or?
Yeah, that's a CPU right there, that's right. And this is a memory module that's chip just below it there. That was a non-volatile memory where I kept the log on all the performance. These are designed to be data gathering mechanisms. And so I could record several months, maybe even almost a year of data on performance of the system and temperatures and stuff in this little memory module. And then I had up here at the top, I had a USB port where I could plug it into a PC and download the data collected by the logging device. These units here, each of these outputs have its own current sensor, and then I have an op amp, an analog to digital converter, and so on. So I can continually monitor all the loads. And if I see loads that are moving out of spec, even close to out of spec, I can anticipate a failure and disconnect it before anything bad happens. Also, it has dynamic load shedding, so that if the power supply should fail and we're running on battery, I can actually detect the state of charge of the battery. When it gets to a certain point, I start shedding loads automatically. And so the higher priority loads are at this end of the board, and low priority loads are down here. And so as the state of charge of the battery goes down, I start cutting off the low priority loads to keep things operating. Lighting being one of the highest priorities. This is the first system we put in Nicaragua up in the mountains. This is Cleo Tilde. He's the father of the family. They have, I think, 6 or 7 kids. This is his house that he built. It's basically just a wooden shack. It's maybe 15 feet by 10 feet wooden shack. And it's just empty inside. When you visit these people, they literally have nothing. And the amazing thing is that with nothing in these shacks, the kids go to school in the morning and they're all clean and neat. Their clothes are pressed perfectly. It takes such pride in their kids and sending them to school to get an education. It's really pretty cool. I played the guitar for a while too on this. So we had a little fiesta celebrating the light. Overhead we have LED lights going on. And this is one of my boxes right there on the wall. We actually gave him a refrigerator too. That system. Now this fellow Tilde, he and his wife volunteered to help with a women's health program in Nicaragua. And so women in the area, within several miles range of his little cabin here, could walk over to see him, and he could measure some vital signs, and he would text those to a cell phone to a doctor, which is actually a different part of the country. But he had a refrigerator that we provided for him where he could store medicines and samples from blood tests and stuff locally. It was all run on solar power. These are some college students that came with me on this trip. This is the first system in Africa. This is the size school I was telling you about to the kids here. And this is really cool because these kids, most of them had never seen an electric light come on. You hit a switch. I mean, they were just so thrilled and exuberant over the whole idea that you could just hit this thing on the wall and lights come on. These kids study long hours too. Their typical school day goes from 7:30 in the morning until 9 o'clock at night. And what they were doing prior to my bringing this IEEE project to them. They had a room, you see that room right there, but they would have a single kerosene lamp hanging in the center of the room for them to study early in the morning or after dark was done. Not very good lighting. So after I put my lights in, they had like 1,000 lumens to cover that space. They put the box in there, up on the roof, put it in the solar panels.
It's really interesting. Like you're sitting there, Butch, and somebody else is putting the solar panels. Just to be real clear about that, okay?
I have some local assistants.
Sidewalk supervisor.
Well, I wasn't sure exactly what y'all were expecting this evening, but I hope you found it interesting. And I guess what I got from Jim was that he wanted, especially the younger people, to get a sense of what's possible in a career in applied science and engineering. There's all kinds of possibilities. Look at that range of things I just talked about, and that's actually about a third of all the different kinds of projects I've worked on over the years.
And you have product everlasting or something? This looks like many life.
Well, I'm 63 years old, and I've been working in electronics since I was 12. By the time I was 12 years old, I was actually my own circuit boards at home. I had oscilloscopes and everything. I had a paper out, and I would buy books in electronics when I was a kid. And that's how I got started. I designed tube things.
So, but you have a very curious mix of skills, right? So clearly you have electrical engineering background, but you seem to bring to the mix, you know,
physics and chemistry. Yeah.
Physics and chemistry.
Well, I studied, for example, like I mentioned, I did a lot of R&D for the military and electronic warfare. When I was working at that company, I was part of a small scrum group, again, really highly talented people, and they were all super smart guys. But to make sure I was the best one, at that time, I was reading 42 journals every month cover to cover. Wow. 42 journals. I would come home from work every day and read for 3 hours every day after work. But my personal objective was to be the best one. That's what it took. So I worked the full day, read for 3 hours every day after work. I would buy new textbooks when they came out in areas of interest. But with the reading that I did, those 42 journals, they were included JAMA, medical journals, they included chemistry journals, civil engineering journals. Basically, I found that the more I knew about everything, mathematics and all the sciences, information theory, all those things were applicable. And so in my last 20 years of career, people come to me with all kinds of problems in any problem domain. And because of the fact that I worked very hard to make my education and experience very eclectic, broad, and based, I can speak to them intelligently about virtually any problem domain. And I do all these medical things.
So clearly, by any measure, you're very accomplished. So how close are you to being the best one?
I would say, no, I would say actually, I probably used to be the best one a few years ago, but I'm sort of like tapering off now, you know. But I would say, again, I have to qualify it in the stuff that I do. This notion of applied science and this problem to me.
I was obviously teasing you, but I have to be absolutely clear you got that.
Yeah.
Now, Butch, what do you read these days? I understand back in the day when you were a crazy kid, you were putting down like 42 journals. Okay, that's just crazy stuff. But these days, in order to stay current, what do you find yourself reading?
Well, actually, I depend on people just like all of you. I go to a lot of IEEE meetings and I talk to all the smart people I can find. And whenever something comes up in conversation that I'm not conversant in, I go home and study about it.
That's okay.
And so right now, I'm sort of like spot studying. So if I hear a conversation about some new compression algorithm, I'll go study that for a little while. And I feel like I'm conversant in that. And so, again, you know, the more I keep abreast of what's happening in all this wide range of technologies, the more useful I am to my clients. I don't want to become the kind of engineer where if all I have is a hammer, everything looks like a nail. You know? I try to make sure that I can do problem decomposition at the most basic level and apply the exact correct solution.
Now, you made a comment earlier about teaching. Add something to that. What do you teach, or where do you teach, or how do you teach?
I lecture at a lot of schools. I get invited to many universities. I've been to USF a few times, and UCF. Basically, you know, in Jacksonville where I live, the faculty sometimes will ask me to come and do some little lessons for them, fill in for them when they're gone or stuff like that. But I'm not interested in becoming an academic in any fashion. But I do a lot of speaking. I speak in universities in different countries.
So I'm wondering, do you take on interns?
That's a good question. Actually, I've had quite a few PhDs offer to work for me for free if I could teach them what I do. But no. For example, people hire me because they've heard about what I can do and they expect certain type of performance from what I perform. And regardless of the people that might come and work with me, I find it that I have a hard time expecting them to perform it the way I would. And so I pretty much do it all myself. Occasionally, I'll subcontract little pieces, but I really enjoy doing it all. For example, many of these projects involve circuit boards and software and mathematics and whatever. I do it all.